Nerding and hoarding. Quick and dirty DIY electronics. Hello, welcome to Nerding and Hoarding channel. Today we're diving into a revolutionary circuit that's been fundamental to all modern computer, the Eccles-Jordan flip-flop circuit. Now you might not have heard the name Eccles-Jordan, but trust me, this thing is everywhere from your smartphone to the most powerful supercomputer. Let's rewind to 1919, back when two engineers, William Eccles and F.W. Jordan, were working with vacuum tubes. Yeah, vacuum tubes, the ancient ancestor to the microchips and transistors of today. In a groundbreaking moment, they developed a circuit that would go on to change everything. And what's really interesting, it all started from a device called a multivibrator. So, as you see right here, we have an actual vacuum tube multivibrator. And as you see, it's a very square wave-ish. And this is what we will try to use later on when we try to build something very strange. Anyway, this is not a flip-flop, this is an astable multivibrator. So the difference between these two is that this just keeps on flipping and flopping and flipping and flopping, while the other one, which we are actually interested in, would just flip and then flop. So let's see, can we make this one flip and flop if we give it some kind of square waves right here? What do you say? Well, I don't know. What do you think? Randy comes feels below. Anyway, it's giving something. Yes, it's actually working better than I thought, which is freaking amazing. Anyway, what happens if you give it a fast square wave? So, you see, we're flipping and flopping, but what do we get out? Well, we get out some noise. Which we love, of course, we love noise on this channel, you know it. Well, back to the story. The multivibrator was a simple oscillator circuit which switched between two states. Now, what does that mean? It creates a signal that flips back and forth, kind of like a heartbeat of electronics. This led to the development of something much more important, the flip-flop circuit. Cut to hosts drawing a flip-flop circuit. Host. What Eccles and Jordan did was brilliant. They modified the multivibrator into a flip-flop circuit which could hold a memory state either off or on. Okay, so this is a monostable, but we need a bistable, which we are not interested in actually here, so we just skip that. Boom, this gave us the first memory storage circuit, a critical building blocks for computers. Cut to host explaining storage circuit, a critical building block for computers. Cut to host explaining the modern relevance of the flip-flop host. The flip-flop circuit is key to what we now call state machines. Basically, any computer or digital device you use is just a giant state machine flipping and flopping between millions of on and off states, or 1 and 2. Not 1 and 2, are you stupid in the head? Or no. But as you see here, the multivibrator is very much not about 1 or 0. It's about a very strange looking wave, which we will build in a circuit. Yes, of course, and make beautiful noise. But the staircase is actually a sound. Back to the story. Cut to diagrams of early vacuum tubes transisting into modern microchips. That way you know that things are working. Alright, host, fast forward to today. The Eccles-Jordan circuit is everywhere, in our phones, laptops, even in space technology. It may have started with vacuum tubes, but evolved into something that lost its heart and is not so very fun. That's why we go back to the vacuum tubes, yes. And the transistor is something that does the job of early vacuum tubes, but on a microscopic scale, and it doesn't need to be heated up. So the host is wrapping it up with some upbeat music. A year over, and you have just begun. So the next time you power your device, think about this. Inside of millions of flip-flops are working hard to make sure everything runs smoothly. Eccles and Jordan might not be household names, but without them, computers as we know it would not exist. Thank you for watching. Nerding and Hoarding. If you enjoyed this dive into history, like and subscribe, and for more tech stories, output music. Anyway, all right, people. So we will not be doing anything more than just flipping and flopping here. So there are two ways we can use flipping and flopping in our noise box. Yes, look it here. So now we have a monostable. It's stable in one state, and this constantly have to get a zap on this pin right here. And what we could do then is use an Arduino or whatever, and we make it control the vacuum tube noise circuit. Or we make it free running, but we will not be able to control very much about actually the frequency. We can change the values here and here. So if we would go about doing something like this, let's see, we take this and this, and we put let's see, input voltage, variable voltage like this. Okay, so look at the frequency. The frequency is what we want to look at here. Do you see any frequency, please? Please give me a frequency reading. So we're getting 111. Let's speed it up a little bit here. And then as we change the voltage here, what happens? Well, you see, it speeds down. So we get a new frequency, which is 74. So this is one way we can control it. Another way is controlling, but it's actually the same thing. But we will just change this value right here and also on this side. Like this. So you see, we are now controlling the we are generating some nasty voltages. Maybe we can use op amps because it's not illegal. Even if we're using vacuum tubes, we can use the best of both worlds. So we started buffering this input here. So we just say this is our CV. All right, CV, and we take CV from let's say from -12 up to 12. Let's see what kind of craziness and noise we can make with this now. All right, so you see we are actually creating noise here, right here. Every time when this green line is moving, it means that a noise is created in the real world. So, and when we turn up the control voltage here, and also I'm going to fiddle around a little bit with these values and also, of course, yes, we are somehow creating some nasty voltages, but we don't have to care about that. What we must care about is changing this values a little bit, because we're not getting values that we can actually read. Anyway, remove the max scale here and just please start friggin' working now. All right. So focus, good people. We have 12 volts control voltage. We're getting 245 hertz. Then when we take the control voltage down to a 6 volts-ish, what do you get? Nothing changes. That's stupid enough. So I take it down even more. I mean, what is going on here? Something is definitely wrong. We are seeing voltages that are 1500. Alright, so we are basically just in a fantasy land here. I have no idea why, but you know. So let's skip this and go back to where we were before. Where we had our triggered motherfucker. So here we were. Alright, so let's see if this is going to work again for us, because you see how beautiful is this. Here we are having 140 here, and we're having 140 there. But you see the shape. The shape is all about what it's all about. You know, the shape. Let's see, we are still getting nasty shapes, but are we still getting the same kind of... Alright, so we're having 400 here, 400 there. If we go down to 44, will that work? Oh yes, it will work. No, it will not work. Yes, it will work. Okay, great. Great. But we're getting some kind of nasty voltage spikes here, so let's say that we would actually put the diode here. Why not, you know? Diodes are good, you know? We can have a diode. I don't care. And then we put a ground here, and we put a voltage here, and we look at this one. So how would you look like, you know? You see? It looks like something totally different. Totally different, yes. And hugely small, if you can say such a contradicting thing. So now we got a totally different signal. You see how totally different it is? 1, 2. We're actually getting sort of doo-doo, 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 doo-doo. So therefore we can also add let's see, how do you do a diode capacitor sort of trigger maker thing? Maybe like this? I don't know, what do you think? Write in the comments fields below. No, it's the other way around. I'm sorry. Why did I do stuff in the wrong way? So, if we take sort of 10 nanos here, and we take sort of remove this and put a little resistor there, just like, well, that's a very small resistor, so we put it like this and like this. All right, let's go. Okay, so it somehow has stopped working here. So if you invent something new that has never been invented, then you will get this kind of results, you know, because now it's saving this and applying for you know, what's it called, patent in the patent office. All right. So we're having some problems here, but who cares? I don't care. Okay, look at this now. Just look at this. How many components do we have? Well, it's not too many actually. And this is totally, is this even being used? I don't know. What do you think? I don't think so. Just delete this. Delete this shit right here. We don't need it. How do you work? Will you work a little bit? Yes, it just goes really, really slow. Why is that? I don't know. Do I look like an expert? Okay, so we're having kind of complexities here. So I'm just gonna do some things that I don't know if it's gonna work, but who cares? I don't care. Okay, we're having something going on here, which is great. um, in the sense that we are getting a harsh sort of spike there. So just remove this entirely because we don't actually need this, but just go with the flow, you know? Look at it. How beautiful is that? There's something wrong here. You know what the wrong thing is? Yes, it says it is really uneven in the speed because it's lagging. You see what's happening there? It's lagging because something is happening really fast and then go. All right, so where was I? Where was you? Where was we? We were here, and this is great, and this is great right there, and that goes in here, and this goes in there. But actually, we don't want to look at this side anymore because there's nothing happening in there. So we want to instead look at this side over here. Yes, of course, like this. Because here is where a rather large thing is being filled up by something. Yes, I mean a capacitor is being charged and discharged right here, you see. This is it. And therefore, we need to look at that place because that is the kind of stuff we're interested in. Yes, but why does it go so fast? That is what we need to learn about now. So then we will sort of change this value right here to enormous value, yes, and this one as well to an even enormouser value. Okay, Fred, now you're a jabadaga. Now, you know what we missed out of? We need actually positive voltage here. Yes, like this. Much better. So, let's go, people. You see what I did? I made it work by just simply looking at it and asking it politely, could you please work? And of course it could. So what is actually the problem now, officer? What seems to be the problem, officer? Is this even doing anything now? I mean, I'm getting very contraceptive now. I am getting so much contraception right now. Is this even doing anything? Yeah, of course it's doing something, but what that something is, only the gods knows. Gods knows? Yes, God has a nose. Didn't you know that? No, but actually, it might sound like I'm just saying babbly babbly, but actually, the thing about this is that I built the exact similar thing, but I think that it was actually not working because it just took the incoming signal and somehow routed it to the output, and maybe it had some kind of filtering in between like this, maybe, you know, because this will also work. See, it will also create something that looks like something interesting. Oh, see how interesting that is. But it's not even using the vacuum tubes at all. It's just a passive high pass filter here, or you know, in the other way around. Maybe there was another place where we had also, you know, high pass, low pass filter. So you know, it's like, how can we know that it's actually the tube that is doing anything? That's the part where I want to learn about. Because you see what we did now? We're doing something here that's like, whoa, this is really interesting, but it's just a passive filter circuit right there. Unfortunately, I might say, but it's not even working now, is it? Why doesn't it look like it's being filtered here? Because it's here. Okay, yes, there you go, beautiful. And what is this? What is this? Ah, so it's there. Yes, beautiful, beautiful. Just remove that because it's only confusing us. So you see right there that I did something beautiful. I create a very interesting looking wave shape, and yeah, but it has nothing to do with the voltage controlled triodes here. Yeah, that's very interesting. Interesting saying of you there, guys. So if we try to invent something new instead of trying to copy something old, how would that look like? Well, it would look like this. We take our input and then we take our triode number 1 and we would put it straight on there, and the conversion is failing. Okay, of course it is failing. Edit, paste, let's see. Okay, it's time to save this because this is the ultimate lag program, so you have to really save a lot because it will crash and all of that oftentimes. So let's see what we can do, what kind of damage we can do, as they say. So let's take this one and put it right here instead. So we are sort of switching places between the high pass and the low pass filter, which is not a big deal if you ask me, but who's asking me? And instead we are making a something that we make sure is fucking up the signal properly, which is because we are doing a double triode amplifier circuit right here. Please work, please, please, please work like this and like that. And now this will be so marvelous, wonderfully, that you could even eat it with chocolate on top if you're interested in that kind of thing. Some people like chocolate, some people like vanilla. At least if you eat it on top. So the very important thing here is that you have two series. No, not serious. Series. Yes, like this. And then we take here, bam, and we take this, bam, and guess what? The last thing we take is, where is our, this one? Yes, we take this one, and let's see. We copy it, copy, and we paste it here. Yes, yes, and yes. There you go. And that is how you build a vacuum tube circuit square wave fucker. All right. View new scope. Please convergence. Please start working. So you see we're getting something, and then it's fax. So let's see what could be problems here. Well, we are having capacitor without resistance right here and also right here. That's just what the program does not like. So we will just simply change that. To here, like this. We can even do also like this. No, wait a minute. Yes, wait a minute. Yes, beautiful, like that. And also like this. So now it's nothing to complain about. Please work. So that's interesting, you should say, and you should nod like you understand anything, but you don't, of course, because you don't understand a single thing that I say to you. All right, and we change this value as well. So let's do like this. I have a good idea. We take this and we take this and we take an input AC sweep here, and we turn. We say okay, we want from let's say from 100 we want to 500 in 1 second. Yes, but we need it to be square wave. So we take what's it called? And yes, I don't really remember what this is called. A comparator, I think so. This is going to work. So view this in the new scope and view this in your new scope and stack them. And let's try to see if we can get that to work. Yes. So we're turning the AC sweep into a square wave sweep simply by pushing it into a operational amplifier, negative, inverting input, and other input goes to the positive input goes to ground. You can probably change them as well. Let's try that because you never know if things are possible, because then we will not change. So now they are in phase, so that's better. Yes. So you could do this to a guitar, it will sound horrible. So let's try this, and so let's see what we do. We have to have an audio output. So let's see, audio output, put it right here, and bam, and reset and run. And now it's gonna run for a full second, which is a huge amount of time if you are a very old program. No, it's not about the oldness of the program. You know what it is about? It is about the complexity of simulating a vacuum tube. It's also about this program. It's not made to be efficient in quick audio. It's made to be a very good program for simulating simple circuits. So you see the gray thing here. When that goes all the way to here, then we are ready. And also you see the little time. Yes, when this comes to 1000 milliseconds, because milli means 1,000th part, and 1,000 divided by 1,000 equals 1. So the interesting thing about this amplifier is that it doesn't amplify, but it shrinks the signal. And that is probably because of this right here, because it's a voltage divider that divides the voltage very much down to 1 here. 1 times 1, it's 2. Okay, let's see. Frequency is gonna come up to 500. So wait for it, wait for it, wait for it, wait for it. All right. So we're closing in, closing in, closing in. I tell you, there you go. We're ready. We play. So we're having the little problem that it's shrinking in power when we are coming lower down, or I mean higher up in the left, of course, because of the low pass filter right here. So what happens if we sort of change it a little bit, and we also change, let's see, so we change it a little bit. Oh, sorry. I'm so sorry. I'm so sorry. I pulled out the microphone, you know. So let's see, where were we? Yes, I changed the low pass filter here. Yes. So let's see what happens with the signal. Yeah, it's where is the output anyways? So that's very interesting. Shape-wise, that is going to really rock. I mean, I'm telling you, people. So this is more like it, I would say. But as you know, this takes about 45 minutes to make this thing. So I will just pause it for now and let's see, can we change something else here? Yes, we can change the power of this one. Yes, by changing the value. But first we have to save and then we change this. No, we don't. So what do we do? Reset. File change. Okay, we have to restart the program now. Yes. So close and then restart. And then file, open file, and there you go. And let's see, where were we? Yes, we were over here where we did some kind of low passing. We can even lower the amplification. But this is the thing that we need to worry about right now. So if we say that this is 2 volts peak to peak, and here is a high pass filter that does something. I can't remember everything by memory purely, but yeah, at least it's going a little bit faster now. And let's see what nastiness we can get out of this bad boy right here. And yeah, so here's 10 nano. Why is there fucking 10 nanos here? Why not one full micro? That's what I fucking wanna know about. What is this doing here? Well, it's only there for the simulation. Yes, I know that. Ah, did you see that? We just did something there, which was very interesting. We have to look at that again. So, when we had the resistor there that is not supposed to be there, then we are somehow making these angles here. So, we are sort of making an envelope here somehow, which is very interesting. So let's do like this instead. Edit paste. So we will have an attack and a release on that envelope right there. Now it didn't work like that, unfortunately. Okay. So let's skip. Let's keep it for now and increase this value here and see if that changes anything. Yeah, that changes the amplitude only. Okay, on this one, what does it do? Or was it that one I was changing? I can't remember. Okay, and this is amplitude there, right there, yes. And how about if we put an extra filter here? I mean, that could be beautiful, beautiful. You know, when I was very young, I found what's it called? And guitar amplifier. So it's called Gorilla, and it sounded just like a gorilla, you know, very much bass. So let's see here if we can get this to work. All right, but we have to delete this one, and this one has to be much smaller, or else we will not get a signal through. So let's see, what is this even going on right here? What is this? What is this even? Hello, what is this? Yeah, let's put a nano there, much better. Okay, and what is this doing here? Please, dude, what the frick is growing on? How about this? You like that? You like this? Nope. Do you like this? Alright, I'm sorry, I've totally lost track of what I'm trying to do here, but you know, that's totally fine. As long as we are making noise box, you know, noise box. Alright, we have finished our 1 second of. Yeah, that's really cool, isn't it?